Uh, First of all, I'd like to thank the organizers for inviting me to speak. The title of my talk is Shimurian Analogs of Barsotti-Tate Groups. The word Shimurian refers to the notion of Shimura variety. In my talk, I will discuss certain conjectures of mine, which are now theorems. They were proved in a recent work by Gardner, Madapusi, and A.Mathew. Once and for all, fix a prime p and a positive integer n. Let R be a commutative ring. All rings will be assumed commutative by default. We are especially interested in the case where our favorite prime p is nilpotent in R. First of all, I have to recall Grothendieck's notion of BTN group over a ring R. BTN is an abbreviation for n-truncated Barsotti-Tate. Let me first explain the format of the definition. A BTN group over a ring R is a commutative finite group scheme G over R, which is killed by p to the power of n, and which has certain extra properties to be listed later. Let me first formulate the extra properties in a very simple situation. Suppose that R is an algebraically closed field of characteristic 0. Then a finite group scheme over R is the same as an abstract finite group G. And we have required our G to be killed by p to the power of n. So G is a module over Z mod p to the n. And we require this module to be flat. Equivalently, in this situation, flatness is the same as being free. This means that G is isomorphic to Z mod p to the n raised to the power of h, where h is a certain number. And this number h is called the height of G. The order of the group G and the height are related as follows. So the order of G is p to the power of nh. And this means that h is the logarithm of the order of the group with base p divided by n. Now, let us consider a slightly more complicated situation when R is an arbitrary field. Let us recall that a BTN group is not really a group, but a group scheme over R. Note that if R is a field, then all commutative finite group schemes over R form an abelian category. Now I have to formulate the requirement for our G, the extra requirement. I will formulate it only if n is greater than 1. Recall that our BTN is a commutative group scheme killed by p to the n, so it is a Z mod p to the n module in the category of finite commutative group schemes. And we require this module to be flat. There is a notion of flatness for objects in an abelian category. If n equals 1, then this condition is empty because C mod P is a field. However, one has to impose a different condition, which was formulated by Grothendieck. This condition for n equals 1 is important because it's a base of induction. But I will skip it. Rather, I give a reference to a short preprint of mine where this condition is formulated. Now, for any group scheme over a field, we have the notion of order. It's just the dimension of the coordinate ring. And now we define the height of G by the formula from the previous slide. Namely, the height H is the logarithm of the order of the group with base P divided by n. It is known that the height is always an integer. Now, if the field R has characteristic P, then there is another numerical invariant associated to a BTN group G, which is called the dimension. It is defined as follows. The dimension of G is the dimension of its Lie algebra. Formally, you can require this even if R has characteristic 0, but in this case, since G is a finite group, its Lie algebra has to be 0. So it's not interesting if R has characteristic 0, but if R has characteristic P, then it is a meaningful invariant. It is known that the dimension D is always not greater than the height H. Finally, let R be an arbitrary ring. And then, let me give the definition of a BTN group over R. By definition, this is a finite commutative group scheme G over R, killed by P to the power of n, which satisfies two conditions. First, if you have any field R prime equipped with a homomorphism from R to R prime, then after base change of our G to R prime, we should get a BTN group in the previous sense. And second, G has to be locally free. In other words, the coordinate ring of G is a locally is a projective R module. Since the group scheme is finite, this module automatically has finite type, and projectivity is equivalent to being locally free. Now, when R was a field, then the height was a number, but now the height is a function on spec R with values in Z. The dimension D is also a function which is defined not on the whole spec R, but on the spectrum of the reduction of R modulo P. And both functions are known to be locally constant. So it is rather harmless to fix H and D, and from now on they will be numbers. Now let me define the stack, which I will denote by BTNHD, and which will be our main object of interest, as well as its generalizations. So we fix non-negative numbers H and D such that D is not greater than H. Definition. Given a ring R, let BTNHD of R be the groupoid of BTN groups over R of height H and dimension D. Of course, this groupoid depends functorially on R. So BTNHD is a functor from rings to groupoids. It's easy to see that this functor is a stack, and moreover, it is an algebraic stack of finite type over Z. And this becomes clear as soon as you unravel the definitions. Indeed, what is an object of BTNHD of R? It's a finite locally free group scheme over R with certain properties. A finite locally free group scheme over R is essentially the same as a Hopf algebra A over R, and this Hopf algebra has to satisfy certain conditions. Now, this Hopf algebra is locally free as a module over R, and this module has fixed dimension. After you fix a basis in this module, the Hopf algebra structure is defined by structure constants of the multiplication map and the co-multiplication map. And the axioms of BTN group gives rise to certain equations and inequalities for these structure constants. So once you fix a basis, you get a scheme of finite type over Z. And if you allow to change the basis, then you get an algebraic stack, which is explicitly represented as a quotient of a scheme of finite type over Z by the action of the full linear group of certain size. So everything was standard here. Now here is a really deep theorem, which is due to Grothendieck. The theorem says that the stack BTNHD is smooth over Z. Now, if you believe that it is smooth, then it is easy to find its dimension. Namely, this is a stack of pure dimension 0 over Z. To see this, it's enough to look at the generic fiber once you know that the stack is smooth. And in characteristic 0, we know that a BTN group is the same as a free Z model over Z mod P to the N. So in characteristic 0, our stack becomes the classifying stack of a certain finite group, and therefore it has pure dimension 0. So once you know smoothness, the dimension is easy to find. Now, here are some bad news and good news. I gave a proof of algebraicity of the stack BTN. And this proof yields an explicit, well, a so to say explicit presentation of BTN as a quotient of an explicit scheme X of finite type over C by an explicit group action. However, this description is useless for almost every person. I would say that it's a bad description. Here are several reasons why it is bad. First, looking at this description, you do not see that the stack is smooth. Second, looking at this description, one cannot even guess the existence of Dieudonné's theory of BTN groups over perfect fields of characteristic P. Somehow, this description has no idea about the existence of Dieudonné theory. And another bad symptom is that if you count the number of unknowns in the system of equations and the number of equations, you get really huge numbers, especially as the prime P becomes large. Now, here is the good. The good news is that now we have a better description, not of the stack itself, but rather of its p-adic completion. This description doesn't have the drawbacks mentioned above. Moreover, this description is Shimurizable. By this, I mean that it admits a generalization related to Shimura varieties. I will discuss this generalization a little bit later. Now, this better description of the p-adic completion was conjectured by me and proved by Gardner, K.Madapusi, and A.Mathew. Before discussing Shimura varieties, let me recall something about the relation between abelian schemes and BTN groups. There is a well-known construction which is the main reason why BTN groups are interesting. Let A be an abelian scheme over a ring R. Let D be the dimension of A. And then we can form a group scheme, Gn. Namely, Gn is the kernel of multiplication by p to the power of n in the abelian scheme A. It is well known that Gn is a BTN group whose height equals 2d and its dimension equals d. Now let AD denote the modular stack of principally polarized abelian varieties of dimension d. then the above construction gives you a map F from the modular stack AD to the stack BTN to D, comma D. This map can be slightly improved. Note that because of the polarization, our group scheme Gn from the construction is equipped with a symplectic pairing with values in roots of unity. And this means that our morphism F admits a factorization, which is written on the slide. So we get a better map, a finer map F prime from AD to the stack, which I denote by BTN to D, comma simp. And the stack is the stack of BTN groups of height 2D equipped with a symplectic pairing with values in roots of unity. Now, the stack of principally polarized abelian variety is a simple example of a Shimura variety. And this Shimura variety is related to the algebraic group GSP 2D. It's natural to expect that our map F prime from AD to BTN 2D, comma simp has an analog for any Shimura variety with good reduction at P. And now one would like to address the following question. What should be the target of this more general map? In other words, suppose that instead of the modular stack of Shimura varieties, we have Shimura variety related to the exceptional group E7. Then what should play the role of BTN groups? The good news is that now we have the p-adic completion of the target of this conjectural map. So I wouldn't say that we already have an analog of the stack BTN itself as a stack over the integers, but we do have its p-adic completion. Equivalently, we know the reduction of the stack modulo any power of p. Of course, one would like to have not only the target of the map, but also the map itself. A group of people constructed it for Shimura varieties of abelian type, but for exceptional Shimura varieties, the map itself is not yet available. Now I have to say something about the construction of the analog of the p-adic completion of the stack BTN. Before describing the construction, let me describe the input and the output, what kind of input we need and what does the construction produce. The input data are as follows. We need non-negative integers n and m, and we need a smooth group scheme G over Z mod b to the power of m. And we need a homomorphism mu from the multiplicative group to G. And moreover, this homomorphism should satisfy a condition which is called one-boundedness. This means the following. If we have a homomorphism from the multiplicative group to G, then we get an action of the multiplicative group on the Lie algebra of G. And we want all the weights of this action to be not greater than 1. If G is reductive, this means that mu should be minuscule. At least if you allow, there is a question whether a zero coweight is minuscule or not. So here I require the zero coweight is allowed. And this is a natural condition because the same minuscule condition appears in the usual theory of Shimura varieties. And this condition is related to Griffiths. In the theory of Shimura varieties, this condition is related to Griffiths transversality. So I describe the input of the construction. The output of the construction is a smooth algebraic stack over Z mod p to the m. And the stack is denoted by bt and mg. And we have compatibility relations as the number m varies. Namely, if you take the stack corresponding to m plus 1 and then reduce it modulo p to the m, then you get the stack corresponding to m. So these compatibilities means that in the limit we get a p-adic formal stack. I would say that you get an algebraic stack over the formal stack of ZP. Now, the important fact is that it's probably not true that in general, this stack cannot be described in terms of finite commutative group schemes. At least we don't know such a description, and there is no reason to expect it. For some pairs, G mu, we do have such a description. Here are two situations when we do have a description in terms of finite commutative group schemes. The first case is when G is the full linear group of order H. In this situation, all fundamental coweights are minuscule. Let mu I denote the ith fundamental coweight. Then if you take G to be GLH, and if you take mu to be mu D, then the stack btn m g mu becomes the stack btn hd tensor by z mod p to the m. In other words, you get the reduction of btn hd modulo p to the n. This is not immediately clear from the definition of btn g, which I will give, but it's a theorem.
And I ask you a question.
I don't hear you well.
Okay. May I ask you a question?
Yes.
Just in this example, doing this choice of homomorphism mu, it means that you Lie algebra decompose on three summands, with -1, 0, and 1, and -1 and 1 are abelian, yeah, subalgebras, yeah?
Yes.
Yeah, and in this case, do you understand that you consider this middle part will be block diagonal matrices, and you get upper block diagonal matrices and low block diagonal matrices decomposition?
Yes.
Okay, thank you.
Yes, of course, another way is to think in terms of matrices. In terms of block matrices. So we can think when you have this mu, we think of matrices of order H as block matrices of order 2, whose blocks have sizes D and H minus D. And the weight spaces of our action of GM are, as Maxime said, one of them is formed by the upper right block, the other is the lower left block, and the zero weight corresponding to the diagonal block, diagonal blocks. Yes. And another example is when G is the group GSP of order 2D, and mu is its minuscule co-weight. More precisely, this means the following things. So we fix a decomposition of our, we have a 2D, we have a symplectic space of order 2D. We decompose it, we choose a decomposition of this symplectic space as a direct sum of two Lagrangian subspaces, and mu is defined so that the weights on the first Lagrangian spaces are 0, and the weights on the second Lagrangian spaces are equal to 1. This is the minuscule co-weight of the group GSP. And for this choice of mu, the stack BTN and mg mu it turns out to be, more or less isomorphic to the reduction modulo b to the m of the stack which appeared, the stack btn to d symplectic, which appeared on the previous slide. Now, let me start discussing the definition of the stack btn mg mu. To define a stack, I have to define its R points, and since this is supposed to be a stack over Z mod p to the m. The ring R has to be an algebra over Z mod p to the m. Now, to give it the definition in general, we have to consider a certain stack associated to R, which is denoted by R sin, and it's called the syntamification of R. I'm using it only as a black box. And the format of the definition is as follows. BTNM, GM, BTNM, the R points of our stack, is the groupoid of G bundles on the reduction of R sin modulo p to the n. And these G bundles have to satisfy a certain condition, which involves the homomorphism mu. I prefer not to formulate the condition. So a theorem of Gardner, Madapusi, and Mathew says that this stack is a smooth algebraic stack. The definition of the stack doesn't use the unboundedness assumption, but the proof uses unboundedness in a very serious way. Without unboundedness, it's not algebraic because even its cotangent complex cannot be defined. To define the cotangent complex, if you know the functor of points, then there is a definition of cotangent complex. But to make everything work, you need some square to be Cartesian. And if you want it to be Cartesian, then certain homology has to vanish. And this vanishing is, for vanishing of this homology, you need one boundedness. So anyway, one boundedness is necessary for the stack to be algebraic. And another, so one theorem of proved by Gardner, Madapusi, and Mathew is algebraicity, and another theorem is the statement from the previous slide, which says that if G is the full linear group, then you get the reduction modulo p to the m of the stack BTN HD. And this second theorem is a modern version of Dieudonné theory. But unlike the usual Dieudonné theory, it works in mixed characteristic, and there are no perfectness assumptions. Now, I had to mention the stack R synt, which is called syntamification. I would prefer to say nothing about the stack. The stack is defined in and discussed in Barth's lecture notes, and these lecture notes are available on his homepage under teaching. So the bad news is that, so actually, let me just say that this machinery of prismatization stack is not really so difficult. It needs, one has to be accustomed to it as usual, and something has to be formulated and proved, and somebody has to write a lot of a long paper. But in principle, everything is not so hard. However, the good news is that if our two integers n and m are both equal to 1, and if the test ring R is smooth, then we don't need high tech to define the stack Btn mg mu. And this is what I want to explain. Everything will be given in very classical terms. Let me mention an open problem. At least as far as I understand, at least it's open in my mind. The open problem is to give an explicit presentation of the stack Btn mg mu, which is proved to be an algebraic stack. So it's a smooth algebraic stack, and this means that it can be presented as a quotient of a smooth scheme over z mod p to the m by an action of a smooth groupoid. And one would like to have an explicit presentation of this kind. This is an open problem. Okay, so let me now discuss the case where both integers n and m are equal to 1. This is our first simplifying assumption. The stack where the name of the stack we want to define is BT11G mu, but let me just denote it by X. Since M equals 1, this should be a stack over Z mod P, which is a field FP. So we have to describe the S points of X, where S is an arbitrary scheme over FP. I will call S a test scheme. Now, my second simplifying assumption is that S is smooth. Smooth test schemes are enough for us because the stack X is known to be smooth. The smoothness assumption for S will allow us to use the classical language of bundles with connections rather than Grothendieck's language of crystals, which has to apply if S is singular. And my final simplifying assumption is that the group G is the full linear group GLH. And this is merely for psychological reasons, because for most of us, thinking about vector bundles is simpler than thinking about G bundles, only for this reason. Now, we have our homomorphism mu from GM to the full linear group. It's a minuscule co-weight, so it's equals to mu d for some d which is not greater to h. So we have two numbers in the story, h and d. Now, let me give the definition of an S point of our stack X, where S is a smooth scheme over Fp. The definition will be quite elementary. An object of X, an S point of X, is the following collection of data. First, we should have a triple L, L prime, L double, where L is a vector bundle on S of rank H, and L prime and L double prime are subbundles. The rank of L prime equals D, and the rank of L double prime equals H minus 2. We can think of a subbundle as a short filtration on L. And one can think of L prime as a Hodge filtration, and one can think of L double prime as the conjugate filtration. So in practice, this is how they appear. The second piece of data are isomorphisms, two isomorphisms, which I denote by alpha and beta. Alpha is an isomorphism between L double prime and the Frobenius pullback of L mod L prime. And beta is an isomorphism between the quotient L mod L double prime and the Frobenius pullback of L prime. In other words, the subbundle of the conjugate filtration is identified with the Frobenius pullback of the quotient bundle of the Hodge filtration, and the subbundle of the quotient of the conjugate filtration is identified with the Frobenius pullback of the subbundle of the Hodge filtration. And finally, the third piece of data is an integrable connection nabla on L with certain properties. The first property is that L double prime is preserved by nabla. The conjugate filtration is preserved by the connection. The second property is that the isomorphisms alpha and beta are horizontal. Here the situation is as follows. So alpha, for instance, let us look at alpha. Alpha is an isomorphism between L double prime and a certain Frobenius pullback. L double prime is equipped with a connection because it's preserved by nabla. The Frobenius pullback of anything is also equipped with a connection. And we want our isomorphism to be compatible with these connections. And finally, the third condition is what I call the Katz condition. This is the following equality. The p-curvature of the connection nabla should be equal to minus the Kudaira-Spencer map. By Kudaira-Spencer map, I mean the following. When nabla is a morphism from L to L tensor omega 1, a morphism which is not quite collinear. L prime is not required to be preserved by the connection. So the extent to which it is not preserved by the connection is a map from L prime to the quotient L mod L prime tensored by omega 1. This map is called the Fourier-Spencer map, and it's already O-linear. So the Katz condition is the equality written on the slide.
So I think you should use also Frobenius apple star alpha and beta.
Yes, you are, in some sense, you are right. So the question is, what do we mean by p-curvature and where does it live? The question is, one has to check that this equality is meaningful. In other words, we are not comparing apples to oranges. So why? So as I said, the right-hand side is a map from L prime to mod to the quotient L mod L prime to tensor omega 1. And why is it true that the curvature is essentially also such a map? And here, some thinking is required. So any person who knows that the definition of p-curvature and who can have several minutes to think calmly can convince himself that this equality is meaningful if the left-hand side is understood appropriately. I would prefer not to discuss this now, but if necessary, we can discuss this after I finish my talk. Now, why I call it the Katz condition? Because it appeared in a paper by Katz published in 1972. Namely, he showed that the data discussed on the previous slide appear in a certain geometric situation. For simplicity, let me discuss a particular case of this geometric situation. Suppose that you have a smooth proper morphism from pi from X to S such that the fibers are curves. Katz doesn't assume. Katz doesn't assume that the fibers are. And let L be the relative one-dimensional de Rham cohomology corresponding to the morphism pi. Then L is equipped with the Gauss-Manin connection, nabla. It has the Hodge filtration and the conjugate filtration. And then, even before the work of Katz, it was known that we had the data required on the previous slides, and these data satisfied it was known that these data satisfied the conditions discussed on the previous slide, except the Katz condition. The Katz condition was new, and it was introduced in the 1972 paper by Katz. And in the introduction of his paper, Katz says that he was very surprised by this equality. And it's indeed a little bit surprising. So maybe more generally, I would say that this stack, so in some sense, the stack was known in the 1970s, except that except that the language of stacks was not generally used then. And also nobody invited other people to study this stack. And by the way, the proof of algebraicity in a paper of mine, which was written before the paper by Katz, by Gardner, K.Madapusi, and A.Mathew, I give a rather simple proof of algebraicity in this baby case where both m and n equal to 1. And the technique used in the proof goes back to the 1970s. Now, namely, the main ingredient is a certain theorem due to Michael Artin and Mill. So everything was ready in the 1970s, but the question hadn't been asked. Just a moment. Something happened. Do you hear me?
We hear you, but we don't see
okay. So the problem is that the system started to install updates. Let me try to say cancel and then see what happens. But the picture still isn't there, I believe. Let me try. There. Just a moment. Please allow me some time. Do you see the slide now?
Yes. First page.
Yes, just a moment. You see the first page, which is already good. Now, maybe I should go to just a moment.
Yes.
Okay. So I already made a historical remark, which says that at least in the baby case where m and n are both equal to 1, everything was ready in the 1970s, but the question was not asked. Let me make one more historical remark. Many years ago, Grothendieck suggested a program which was called crystalline Dieudonné theory. It was developed in an important series of works by Berthelot, Breen, and Messing, and I think there was also a work by Maser and Messing. And now one can ask, what is the relation between the recent work by Gardner, K.Madapusi, and A.Mathew and crystalline Dieudonné theory? As far as I understand, they definitely use some important ideas from crystalline Dieudonné theory. On the other hand, as far as I understand, they do not rely on the results of the crystalline Dieudonné theory in a serious way. In other words, as far as I understand, the theory developed by Gardner, Madapusi, and Mathew supersedes crystalline Dieudonné theory. And this is good news for humanity because the number of pages is much smaller and the result is strong. But of course, Berthelot, Breen, and Messing did a great job, which was important, very important. It looks like now we have a better modern version developed by Gardner, Madapusi. Okay, I have finished my talk. Last but not least, I'd like to congratulate Maxime on his birthday, and I'd like to wish everybody. I want to wish all participants of the conference, but especially Maxime, to be happy.
Thank you. Questions? Yes.
So just to make precise what you said about the GSP case, where you say that you get almost, you had some in parentheses, you get almost the stack of Barsotti-Tate with alternating pairing. So what does this almost mean? Maybe you said it in the talk, but I did not.
Okay. I'm a bit tired. So it's something related to the difference between GSP and 2SP. I would say this is what I think I can answer. I think I can give a more or less precise answer to your question. So we have this sophisticated stack corresponding to GSP. Now, GSP maps to the multiplicative group, obviously. This sophisticated stack corresponding to GSP maps to the stack corresponding to the multiplicative group. Now, this stack corresponding to the multiplicative group has several connected components. And the stack defined in terms of Barsotti groups with alternating with a skew symmetric pairing corresponds to one of these components. In other words, almost is due to the difference between the symplectic group and the GSP.
Okay, and then in the last sentence, there were two words, alternating and skew symmetric. It is not the same when p equal to 2. So which one, are they equivalent here, or is there some difference between those conditions?
I require the scalar product of x and x to be 0. Is it skew symmetric or alternating? I don't remember, but anyway, the stronger condition.
Okay.
Maybe just.
Actually, I cannot. I can let me add that I cannot bet my life. If p equals 2, I cannot bet my life about what is true, and especially about what has been checked by Gardner, Madapusi, and Mathew. So maybe one has, for safety, let's assume that P is odd.
Maximka's question. Yeah, I have a question. Yeah, is that roughly what you're speaking at? When you have geometric variation of hot structures of some dimensional number field and Mumford-Tate group of Shimura type, you say something about p-curvature and this when n equal to 1 and some extension of this of p-curvature. But there are variation of hot structures which are not of Shimura type. Is any word?
Just a moment. I don't when you say variations of Hodge structure of do you really mean non-Shimura? If it's not Shimura type, then what is the question? I don't quite understand.
Yeah, no, but all the story it's about like p-curvature for Shimura type.
Yes. So let me say it this way. So first of all, Shimura varieties are very mysterious. At least they're mysterious for me, but I expect that they are mysterious for everybody. Many years ago, Winston Churchill said something about Russia. He said that Russia is an enigma shrouded in mystery and maybe something else. And I'm not sure that Russia is so mysterious, but Shimura varieties are very, very mysterious. And the problem is that for exceptional types, E6 and E7 and some of DN types, we do not really understand them. They are defined using complex algebraic geometry, and then you have to work hard to prove that they're defined over a certain number field, and then you have to work hard to construct integral models. And moreover, these integral models, the existence of good integral models is unknown in general. So what I did and what Gardner, Madapusi, and Mathew did was to pretend that everything is fine. That, suppose we know that Shimura varieties exist, that good model for them exists, and they behave as expected. Then it is clear that we have to, that on this modulo P, that on the reduction modulo P, we should, well, I would say it this way. We know what kind of structure we have on the reduction mod P of the modular stack of abelian varieties. And now you can, when we look at the structure, you can formally replace the symplectic group by any reductive group equipped with a minuscule coweight. And then you get a certain structure, and we can axiomatize the structure. And this is the stack which I denoted by script X. But there is another question of but at this moment, we don't know in general that, we don't know in general that the Shimura variety indeed has good reduction in the cases when it is expected to have good reduction. And B, we don't know whether the on this reduction mod P, we indeed have the G bundle with connection and with two reductions to parabolics satisfying the axioms. So this should be true, but it's still unknown. But the approach of myself and Gardner, Madapusi, and Mathew, it was to bypass this these complicated questions related to Shimura varieties. Now, Maxime asked, what if we have not a Shimura variety, but an arbitrary variation of Hodge structure, or maybe a variation of geometric origin? But then I don't understand the question.
No, that's no precise question, yeah.
Yes.
Okay. So if there is more questions, you can ask. Yes.
Speculative question.
Huh?
Does it help in the Lagrange program?
I don't hear. I don't hear the question. I don't hear anything.
I wanted to ask a speculative question. Does it help in the Lagrange program?
So the question was something. I heard the word speculative, which is quite okay, and I heard the words Langlands program, but I didn't hear the other words. What was the question about the Langlands program?
Is this helpful for Langlands program?
The question is whether this could be helpful for the Langlands program. Hopefully, yes, but here, well, for me, the motivation is not, my motivation doesn't come literally from the Langlands program, but rather from the following fact. The Shimura varieties are, I heard about Shimura varieties in my youth because I attended lectures and seminars by Piasecki Shapira. And I know, I didn't understand much, but I know that the Shimura varieties are very, very mysterious. On the other hand, I spent most of my life in characteristic P, where and Shimura varieties have cousins in characteristic P, which are called the modular stacks of Stukas. They were introduced later than Shimura varieties, but actually they're simpler. And they're not as mysterious. At least the definition is simple, and you don't have to struggle to prove the existence of good models and so on. You don't have to deal with analogs of complex numbers. So, my motivation is that I'm puzzled by the fact that the Shimura, the modular stacks of Stukas are so simple in some sense, and the modular stacks of the Shimura varieties are so complicated and I would say inaccessible. And now the good news is that we have prismatic theory, which, yes, and maybe another thing which I didn't mention, but of course it's clear to almost everybody in the audience, maybe everybody, is the following. So the philosophical definition of Shimura variety is that Shimura varieties parameterizes G motifs, so to say, where G is our reductive group. The problem with this, so this is a great heuristics, but the problem is that we don't really know what a motif is. But now we do know what the p-adic realization of a motif is. And this is given by prismatic theory, which was developed first by Bad Morrow-Scholze, and then when it first appeared, I thought that I will never understand it because I have to learn a lot of algebraic topology. Then a much simpler version due to Bad Scholze appeared, which didn't involve algebraic topology, and then the Sterke approach to prismatic theory appeared, which made life even simpler. And so now we have a pretty good understanding of what a p-adic realization of a motif is. And so if we're interested only in the p-adic shadow of Shimura varieties rather than of Shimura varieties, then we can do something using prismatic theory. And this is what I use to formulate the conjecture, and what Gardner, K.Madapusi, and A.Mathew used to prove them. But of course, there is a more serious question about what the question is, what is there a better approach to Shimura varieties than first defining them as complex varieties, then proving that they're defined over a number of fields, then using all possible and impossible means to construct integral models and so on. So this approach makes me very unhappy. And one can ask whether there is a better approach, but I have no idea about this. Yes, but fortunately we can now work pretty well with, so to say, p-adic shadows of Shimura varieties.
Okay, thank you very much, Volodymyr.
Thank you for inviting me. Bye-bye.